Hello. In this video, we're going to take a look at ways of using Taylor series to help us evaluate limits. So we're going to take a look at one problem here, and that's this one. Let's find the value of the limit as h goes to 0 of h to the fifth times e to the h minus 1 over 1 minus 2h squared plus 2/3 h to the fourth minus cosine of 2h. Now, as always with limits, we first check to see what form we have. You can see that as h goes to 0, the numerator and denominator both become 0. So we have a 0 over 0 indeterminate form. We've worked with these for a long time. We started these first week of Calculus 1. We sometimes solve these things by factoring and counting like terms, maybe using known facts about trigonometric limits, multiplying numerator and denominator by a conjugate, or even using L'Hopital's rule. In fact, this limit can be done by L'Hopital's rule, but it takes 6 applications of the rule. After the first 5 applications, you're still going to have a 0 over 0 indeterminate form, so I'll have to use the rule again. After 6 applications, that numerator gets pretty long and complicated. We're going to take a different approach. We're going to use power series, and the power series approach works something like this. We're going to notice, first of all, that because we have h equals 0, we're going to express the numerator and denominator as Taylor series at the point, expansion point x equals 0. If this had been something different, like perhaps h going to maybe 3, we'd then probably use a Taylor series about x equals 3. Okay. Generally, most of the examples you'll look at will probably have h going to 0. So you can use Taylor series about 0, which we also call Maclaurin series. Okay. So our approach is going to be the following. We're going to take a look at these limits, the Maclaurin series shown on page 620 of your textbook, and use those to write the numerator and denominator as Maclaurin series. Then we'll show we can do some algebra to resolve the limit pretty easily here. So we're going to start with the numerator first. So we're going to find we're going to look up, say, the power series, the Maclaurin series for e to the x, and substitute h for x in that series. We do that because everything's in terms of h in this thing we want to look at. We're then going to subtract 1 in the numerator and then multiply that whole result by h to the fifth. So here's what that looks like. So up here we see, here is our series part. So there is the series for e to the h, that is e to the x with x replaced by h. We then subtract the 1, that's what we see here, and then we have the h to the fifth multiplier in front. So when we combine terms inside the big parentheses, the outer parentheses, we see the 1's cancel, which leads us to this term. And then next we can multiply this h to the fifth out in front, like we would with a normal polynomial, multiply it inside the power series, which we think of as a polynomial, multiply each of these terms by h to the fifth. And so we add 5 to all the exponents in that series expression to get what we have here. Finally, in anticipation of taking the limit as h goes to 0, we're going to factor out h to the sixth from each of these terms, because all these terms have an h to the sixth in common. And factoring that out gives us the expression down here. So later on, when we go to evaluate the limit, we're going to replace the numerator by this expression. For the denominator, we are dealing with a cosine function, cosine of 2h in fact. So we look up the Maclaurin series for the cosine function, and here it is, again from page 620. And now we're going to replace the x by 2h in this function because the original limit deals with cosine of 2h. So I like to think of these Maclaurin series or any series identity like this as a template. I can replace the x by anything I want, as long as I do it consistently on both sides of the equation, and that'll give us another true identity or another true series expression. So down here, I've replaced the x by 2h everywhere I see it. That's all we've done. No further algebra or anything like that. And so now we have a series for 2h. And in the next step, we just do a little simplification, expand the 2h powers, and then do some arithmetic to cancel with some factors in the factorials in the denominator. Now we aren't done because that denominator was a bit more complicated. We had the cosine of 2h subtracted from this polynomial in front, this 1 minus 2h squared plus 2/3 h to the fourth. So here we've copied that denominator, and we see right here we've put in our series for the cosine of 2h, the one we got on the previous slide. And now again we just do some arithmetic. We treat infinite series often like just big polynomials. When I have to add one polynomial to another, we add or subtract coefficients of like powers of h. So the two 1's cancel, and the minus 2h squared with a minus 2h squared, those cancel, and likewise the h to the fourth powers expression cancels. And that leaves us with this expression here. Notice it's just the tail end of this series, and then the minus sign out here, we have to factor that in, and so that gives us a plus 45 h to the sixth, etc. Once again, we factor out h to the sixth because we anticipate we're going to do some factoring and cancellation later on in the work. So here is what the denominator now looks like, and this denominator is going to go back into the series. So we're now in a position to evaluate the series very quickly. Here's the original series, or the original, limit. And there is the expression we found, the series expressions for the numerator and denominator. Just copied them down from earlier work. And this h to the sixth factor just begging to be canceled. So once we cancel this, we're in a position to evaluate the limit. So we now see we have a numerator in the denominator. As h goes to 0, neither of those becomes 0. Now as h goes to 0, all of these terms go to 0. Similar for anything in the bottom with a power of h involved. And we're left then with just 1 over 4 45ths for an answer of 45 over 4. So once we got all the series in place, this was a pretty quick problem. And the nice thing about this series is we're able to quickly reveal this h to the sixth factor that we had to get rid of, and which would have taken 6 applications of L'Hopital's rule had we gone with that method. So what are the takeaways from this video? Well, we used algebraic operations, algebraic skills to manipulate infinite series. This is a very, very important idea, and one that will help you manipulate series, form new series from ones you know, etc. Particularly, we use substitution. We placed x by h in the exponential series and x by 2h in the cosine series. We use addition and subtraction to cancel some polynomial terms in the denominator. We factored. We got the h to the sixth factor out of both series. Then we did the cancellation. So a lot of the same operations you used with limits before, the kind of things you did to simplify. And so once we had a non-zero or zero form, it's kind of one of those common sense limits, we could get our answer of 45 over 4. So if you're careful with the series, this should be a pretty quick and efficient method for evaluating some rather complicated limits. Thanks for listening. Bye.